it has one less electron. So photoelectron emission current is a positive charging current. And then another charging current is, let's say that dust is just sitting in the plasma. There's ions and electrons. So if an ion hits, it's charging positive. If an electron hits, it's charging negative. And so these can balance out. So this is the ion and electron collection current. And then there's another current that happens, which is if you have a really high energy electron, it can release from the thin surface of that dust electrons. And because all of these particles are released, these electrons, it's a positive charging current. And so these are the main ones in the Jupiter system that we are concerned with. And so just go through and you add up, you have to take into account what the plasma looks like, you take into account what the strength of the UV photons are, and then there are equations for the electrodynamics and the charging, and then you put in the magnetic field and you move the particle. So this is, you might not be able to see this back there, it's a little bit small. But the forces that are on the dust is a gravitational acceleration, okay, due to Jupiter. There's the light pressure force, okay, due to the sun, mostly. There's a Lorentz force, okay, that's due to the electrodynamics in the environment. And then there's the solar gravitational force is this one. And this first one is Jupiter gravity. So there's two gravity forces in this. And so Lorentz acceleration, this will look familiar to you probably. So people, when they model and simulate the dust, often they take the Q, the charge of the particle, and they make it fixed. But in fact, as it's moving through the plasma, it shouldn't be fixed. It should be changing all the time. So about 15 years ago, Mihai Huranian, my advisor's colleague, put together his first simulations that always had this changing in time. So if you're computing this numerically, you always want to make sure that as you calculate the accelerations, that you're also changing the charge at the same time. So just, you don't want to leave this as constant. You want to always have this change as well. And then the gravitational acceleration of the sun is that. So now this tells you more why the varying charges matter. On the left here's starting a particle from Io where the particle is fixed at 3 volts. And then these are different sizes, 7 nanometers, 8 nanometers, 9 nanometers. See how small these are? And when they're larger, then gravity keeps them inside. When they're smaller, they act like ions, and so they just move like in trajectories like this. And then in between is when they have a window to escape, in between sizes. Now this set of plots here is when the charge is allowed to vary and calculated in a numerical way, so it's not fixed. It's collecting ions and electrons and UV photons and all of that, and so the charging is determining how a trajectory moves. And this is a side view. This is a top-down view. This is a side view. And this is a pretty large view of the inner part of the system, 20 Jupiter radii. And let's see. And also more about how the varying charges matter. So this is a side view from 10 Jupiter radii to 100 Jupiter radii, and each of these little numbers represents the size of the particles in nanometer. And so the larger ones are really heavy, and they're not accelerating very fast. But the small ones are accelerating, and then they have a long tail acceleration, and roughly about here is the edge of the system, of the Jupiter magnetosphere. Now, here's the variable charge, here's the fixed charge. If you have the charge allowed to change, it accelerates faster, and it stays, and it keeps accelerating longer. And so this is something I also explored in my thesis, is that I needed to make sure these particles' charges were varying because they were accelerating and escaping the Jupiter system much faster than other people were imagining they should. And then this shows, this is red, and so the particle starts out negative charge, this is the potential of the particle in volts, And then as it's in the Jupiter system, there's the charging current that's most dominant is the secondary electron emission current. So high energy particles from the Jupiter plasma are hitting the particle and charging it more positive, more positive. And then finally, so it goes from negative to positive here. This is 5 nanometers and 8 nanometers, and then it can escape the system. So this is that window that the particles can escape. And this is a top-down and a side-down view, too, of how the trajectories change and are objective. The C here is just one path to Cassini. There was a very nice dual spacecraft measurement in 2000 where Cassini was flying by Jupiter on the way to Saturn. And so Jupiter had Galileo inside, and Cassini was outside the magnetosphere, and the two had a dust detector. So there was a nice measurement with the two spacecraft where they were pointing in the same direction and collecting dust, and we were trying to calculate what trajectories could go from one spacecraft of dust. Okay, well, when it hits Galileo, then it's ionized and destroyed, but there's many of them, and then some of them would reach Cassini, and which are the sizes of particles and what would be their charge, their potential. This is about 6 volts. The particle would reach Cassini. And the speed of travel is about 250 kilometers per second. Very, very fast. It's as fast as a solar wind. So these particles are really, really fast. Now, I might skip this. One of the things you can do in the modeling is you can vary what composition your particle might have. But the problem with dust physics, and maybe I would like more lab exposure and experience, is there are not enough measurements for these parameters like secondary electron emission. So if you hit a particle with a high energy, with a lot of energy, and its composition is silicate or aluminum or something, what are the number of released electrons you get from that? And there are not very many lab measurements for this. So you go to the CRC Handbook of Chemistry and Physics and you look up some tables, but they're really old. They're like 50 years old, these tables. And so I hope people associated with my field are considering more lab measurements because we need them. So these are just from Chemistry Handbook of Physics, and also from a few labs that have made measurements for secondary electron emission. And this shows what kind of behavior you would have if you imagined that your particle had silicon oxide or sulfuric oxide and silicon oxide, two composition. And I determined the composition by just looking up in the table and saying, okay, this is what the secondary electron emission is if the particle was this. And then I run my simulation, and then I put another composition. And then you see that its dynamics is a little bit different. It escapes with different sizes of particle and with a little bit different charge potential. Okay, I think I missed it because we need to move on. So I'm going to wrap up the Jupiter dust streams and just have a fly-through of what some of the trajectories would look like. It would remind you a little bit of comet dust tails, probably. So what happens in dust physics, because it's dominated by electrodynamic forces, is that different sizes of particles are coupled to the magnetic field so that when it's released, all the particles that are of one group of sizes, for example, would have one behavior, and all the particles of another group of sizes would have another dynamical behavior, and that's just due to its size. So because the different sizes are being filtered in this way by the magnetic field, any large magnetic field, like Jupiter's magnetic field or the solar wind, actually acts as a giant mass spectrometer to separate the particles. And so if you find this glorious configuration of dust particles, you would bet that if it's a very dusty environment, it's being separated by the magnetic field in a way like this, due to just the fact that the different sizes are affected by the electromagnetic forces in a different way. So I tried a couple of experiments where I released all my dust from a ring, and this is what you get after running it for about 8 hours, 8 hours in particle time. And then if you release, let's say you have IO moving and you just want to have it as a segment, this is the kind of configuration that you get. And the colors probably are not very clear here, but I have them color-coded by particle size as well. And I'm just going to fly through a little bit so you can see how varied it is and how much it looks like a mass spectrometer, the way it's separated. So over the top here, this is the ring configuration, I think. Yeah, this is the ring. And then zooming in to the left and zooming in to the right. And each of these are different sizes of particles. And then zooming in more, and we're going to finally enter what that looks like in the center. Okay, so these particles in here are trapped, and these won't be escaping from the Jupiter system. They're too small. So these are the smallest sizes of particles, probably about 5 nanometers. Okay, well, Jupiter is not the only one that has dust streams. Saturn does too. And these were discovered as Cassini was on its way to Saturn. So at about 2003, 2004, it arrived 2004. And so what Saturn saw is that Cassini saw whenever Saturn was in the field of view, it got more impacts. But it was, because it's got this funny directionality, it doesn't have a scan platform where it's scanning all the time. You know, you have to be careful that you're filtering out the field of view and you're looking where you want to look. And so when the directions were sorted out of the Cassini dust detector, we have bursts of impacts like this. And moreover, when it was approaching Saturn, these bursting parts seemed to be correlated when the interplanetary magnetic field strength was in a compressed zone. So you may have heard that the interplanetary magnetic field is kind of a warped sheet like this. And so there are these compressed rare regions and then expansion in regions like that. And so in the compressed regions, it turns out that the dust streams were stronger there. So this was a big clue that the way the magnetic field is directing the dust particles, and they're forming the streams. So we've gone beyond what is the source. Now we're thinking about how are these dust streams formed. But the Saturnian dust streams, we don't have a moon like Io. So what is the source of those dust streams? Let me skip this for just a moment. So for Jupiter we have Io, but for Saturn, what are the sources for these dust streams? Well, some were speculating that the dense rings could be the source as meteorites impact onto that outer part. And then others were looking to Enceladus' plume, which was discovered about the same time. And then, well, the E-ring is a huge ring. It used to be the largest ring of Saturn. Now there's a larger one. But the E-ring particles fill the area around Saturn, and this could be a source of the particles too. So several PhDs determined, not mine, but others that followed me, that the most favorable dust stream source is the E-ring particles, and that you have to have a very special magnetospheric environment, so you have to have this kind of compression mechanism to compress and form these dust streams. And the ejection mechanism is still being studied, and that's why this is one of the PhD students, well, he's now a postdoc. It's very interesting. He spent maybe 5 years studying this, and so these are his words. And then the E-ring dust, which are larger particles than what the Saturnian dust streams are, there's another mechanism that arose these particles smaller and smaller, so it's called sputtering. So the plasma environment around Saturn is causing these particles to chip off and to erode away so they become smaller and smaller and smaller to be the small size that you need to have to be coupled to the Saturnian magnetosphere. So that's another mechanism we have to have for this. Whereas for Io's dust, they're already small. They're very small, but the E-ring dust are much larger. They're 1 micron or so, a little bit larger even. Okay, so now this topic here is going to be just a discussion with not a lot of analysis because I'm in the middle of the analysis. So this idea is that there are albedo patterns on the mid-sized icy moons of Saturn that are very odd. You can't explain them if whatever hit those moons came from outside. And so people were looking at the orientation, because as the moons travel, you have the ram direction and then the tail direction, and what could be hitting from these different directions to make these splatters to look the way they do on these mid-sized moons. So it's Dione and Tethys and Enceladus, Rhea. And so my research topic that I got funded was to look at E-ring dust as the mechanism, the source of the dust to splatter it. But I have to whittle it down and sputter the particles to make them small too. So then, let me skip that. So there's leading and trailing sides, and this is a kind of a division between redness and the different filters of one of the cameras. And these are albedo patterns. And so let's see. Yeah, Tethys, Mimas, Dione, Rhea is down here. Yeah, okay, Mimas, Enceladus, Tethys, Dione, Rhea. So the ratio of the infrared reflectance by the ultraviolet reflectance is what we're seeing here. And there's some strange banding and patterns that are appearing when you do this kind of ratioing of the filters. And moreover, some of the craters look like they're brighter on this side and darker here, so they're impacting from a particular orientation. And then there are dark patches like this, and so these are the features, the albedo features that I'm trying to explain. And so right now I have simulations running, and then I have a photometry expert that's going to work with me, and we're going to try to look at if you have the surface, the regolith of these moons, be a particular way, can you get these kinds of patterns? So here's Dione with trailing side, leading side, a crater that's painted, so this is brighter here. And this just shows some of the albedo patterns I'm trying to explain. And then Rhea has, let's see, has these wisps. So this is trailing, this is leading, and these wisps here, the wispy streaks, and I'm not trying to explain these so much, I'm trying to explain these dark patches here with the trailing and the leading side. Okay, and then Iapetus. So Iapetus has a strong contrast in albedo that's due to a totally different reason that I'm not going to study in my study, but there are also some craters that are painted in the way that I showed before too. Okay, so future work, this is something that I really want to get funded. I've submitted it 4 times already. I'm getting tired of submitting it. Now I'm taking a grant writing class, so I can have an excellent proposal, and it won't be refused. That's what I'm hoping. And so this idea is that there are no magnetic fields around asteroids. You have an airless body. It's embedded in plasma. It's embedded in UV photons, and each one of the spacecraft that have visited asteroids, like Dawn saw Vesta's regolith that was glorious. That you could see landslides into craters, and Rosetta, when it passed Lutetia, saw landslides, and it seems like there's regolith everywhere you look on these asteroids. So if there's regolith, they've got to have charged particles. Now, what size of particles is that regolith? That's the key question. So the first step in this analysis is to determine what is the range of particle sizes you can imagine for the regolith of asteroids. And is there a population that are micron and smaller that you would bet, it must be that it's charged up by all the mechanisms that charge up these other particles, so that you can have levitation. So you do have terminator, you have a difference in light and dark from sunlit side to dark side. You have craters that are also dark and shadowed and light. And so every time you have a difference in these light regions, there should be levitation happening. And well, astronauts are proposing to go to asteroids. And now you have about 4 space companies, private, that are let's see, have you heard about some of these? Yeah, there's, every time, it seems every month, there's a new company that wants to mine the asteroids, and now there are 4 of them. And they each have a different business plan, and they each claim that they're going to be hugely profitable, but I'm not sure how they're going to, they have to do a lot of building in order to get there. But one of the things they're going to need to worry about is if their equipment has charged dust obscuring their lenses, for example. Because if you're on the surface of any of these, this dust are going to stick to your suit, and it's going to stick to your equipment, and it's going to be a hazard for you. In addition to having great physics, it's also a hazard for people who want to walk on the surface of any of these things. So I can use that in my proposals too. I can say, well, we need to make sure we protect our astronauts, but I also want to know how the dust moves. So that's my future plan, and this shows some of this was Lutetia, from Rosetta Iris, and there's a landslide right here. So these are 3 different craters. This is a crater that's been filled in by a landslide, and here's another one right here. So there's a lot of regolith there, and regolith is not an easy subject either. You know, the geologists will have a lot of questions. Well, what about 1 meter down, and what about the density of the particles inside the rock? And so you have to actually break down what are you calling regolith. This is all regolith, and then you have the density of the pieces inside that. And then if you want to do a good job with determining the properties, you have to combine radar and infrared measurements and optical polarimetry to understand all of the size, the density, those are the 2 main ones. And once you have that, then that can be input into my simulations. And so these are the asteroids I want to study for different reasons. Vesta, Lutetia, and Eros, and Gaspra, and Steins. Steins is a Latvian astronomer, of course you know that. But not very many Americans know that, but I know that. And Itokawa, and then Pallas, and Psyche, and Daphne, and Sirius. So some of these, for example, I think, which is one I'm thinking of. I think Lutetia is the one. But there's one of the largest ones is its orientation is such that it's in sunlight for a good part of the year. And so if it's in sunlight like that, imagine what happens once that sunlit side turns to darkness. You're going to have enormous electric fields built up from that difference in the charging of the particles there. So there are some of these asteroids I want to study more just because they have interesting orbital characteristics that would make the charging of the surface even more interesting. So that's it.
Thank you very much. So, we have time for some questions or comments, please. Yes,
at the beginning of your presentation, you mentioned the dust around the Earth.
Yeah.
And you told about it like it's a problem. I wanted to ask, how is that a problem?
Well, it depends how big it is. So if it's like centimeter size, that can damage your instruments on a satellite, for example. So I'll tell you a story. There is a New Horizons spacecraft going to Pluto now, and it's going to arrive in 2000. 14, 15. Rosetta and New Horizons are saying you're 15. It's going to arrive in 2015. And so, as it turns out, Pluto has 5 moons, and these are just discovered in the last year. And because of this, there is now a good assumption that there's a lot of particles and debris, natural debris, impacts. There's enough generated material from impacting onto these moons that centimeter-sized particles could be a problem. And they'll have particular trapped resonant orbits. And so what the New Horizons people have spent their last year doing is coming up with alternate trajectories for the spacecraft. They call it the Shabbat Safe Haven Bailout Trajectory. So if it turns out that the camera is detecting a dusty area, I don't know, they're finding that they're going into an area that has got more particles than they would like. They're going to change the trajectory. So just because even centimeter size can just destroy the spacecraft. So you certainly want to be aware about it for that reason.
Thank you. More questions? Yep, please.
Thank you very much for coming to your father's land. That's first. And thank you for a very interesting report. But I'm, as a former solid-state physicist, I have a question. Are there any ideas about the structure, about the content of these particles? These are material particles.
Yeah.
What's inside of these particles? What atoms, maybe molecules even, or what's inside?
Well, probably carbon and silicate based. I mean, the composition was what you would what you're finding when you're doing spectroscopy of meteorites. And so all of the compositions that ordinary chondrites, what are those? Oh, there's tungsten and I mean they know the composition of that. Now dust particles are agglomerations of that. Well, I lived in Rome for a while, and I looked at these buildings, and you could see the periods of history in the buildings, so that you had the 2,000-year-ago period, and then the Renaissance period, and sometimes one building had 5 periods of time in support structure, and so dust particles are kind of like that too. That the original is something that was a chip of a asteroid or meteorite, and as it formed in space, it was accumulating gases and it growing in that way too. I mean, that's our planets, our terrestrial planets, and the gas giants too, were formed starting with small dust that then grew by accelerated processes and gravity and got larger and larger. And so but the smallest dust particles are just agglomerations of stuff, and you can put them in the lab and you can measure its composition and its properties. So
Are there some results already from such experiments?
Yeah. There's large collections of dust, like in Houston, they have a large dust database that there were collectors flying under the wings of aircraft in the higher atmosphere in the 1980s that were bringing back, these collectors full of dust, and those went into the collections. And there are regular expeditions to Antarctica. They take the ice and they melt the ice, and they collect the tiniest micrometeorites, and then they put them in the collections, and they analyze that with the instruments. And then you have stardust that had that gel material that collecting interstellar particles and interplanets. So we have real dust that we can study in the lab, and from these scanning electron microscope that it has a chondrule here, this kind of round silicon thing, and then it has this other rock material around it, and you can slice through and see all these different parts of its formation.
It's amazing. Yeah.
Thanks for your talk. I have 2 questions. The first one, what is the reason for these dust particles to have such large velocities? And second one, I understood one kind of problems you have considered it is motion of charged particle in some kind of non-homogeneous magnetic field of some celestial body as Jupiter as well. Are there some collective effects for these ensembles of dust particles?
Yeah, so the large velocities is just accelerated by the magnetic field. So they really do act like ions.
But magnetic field cannot.
Well, okay, right. It's the force of the electron.